Okay, hello and welcome everyone to another Applied Flow Technology webinar. Good morning, or maybe good afternoon, or even good night, depending on when you're watching and where you're joining us from. My name is Nick Vastine. I'm a business applications engineer here with Applied Flow Technology. Looking through the attendance list, it looks like I've worked with a lot of you guys before, so I'm glad you guys are attending the webinars and finding some value. Today's topic, we're going to be looking at the Scenario Manager in pretty great detail, sort of starting from foundations and introductions all the way up to our different analysis options. So the name of the webinar is No Stone Left Unturned. How can we exhaustively analyze our different alternatives using that Scenario Manager to our advantage? So without further ado, we'll jump into our agenda. So the first thing we're going to do, again, starting from kind of engineering foundations and engineering concepts, is what are scenarios and what are some examples of cases we might want to evaluate in our hydraulic system. We'll look at evaluating alternatives, considering multiple operating conditions during design, sensitivity to different variables, and then how we can use scenarios to troubleshoot problematic systems. We'll take a look at how the Scenario Manager itself works. So one of the big advantages of using the Scenario Manager is this inheritance structure, which we'll go into sort of as an introduction. It won't be comprehensive, but it should give you a basic foundation. And we'll go through an example looking at an experimental design where we're going to be sizing some pipes for a cryogenic transfer system. With an understanding of how the Scenario Manager works, we'll look at some of the tools and features that we have surrounding scenarios to help users manage them. We'll look at how we can compare different scenarios, both input and output, how we can isolate different scenarios to individual files. So one of the appeals is scenarios manage all these different cases in a single file, but it's useful to try to isolate them. And then as we build out our infrastructure and different scenarios, how can we batch run them to run them in sequence instead of babysitting the model, running one, looking at the output, running the next one, so on and so forth. Finally, once we've generated all of our output, we'll look at some options for analyzing that output. So we'll consider multi-scenario output. We'll touch briefly on multi-scenario graphing, more just to bring awareness since the interface is pretty intuitive. And then we'll touch briefly on Excel export, but we do have another upcoming webinar that will go into that in much more detail. So that won't be the main focus of this webinar. Again, if you've never touched scenarios in any of your models, this should give you a good baseline, and then we'll go through some of the process and features and tools that we have to help you manage them and analyze them for your own system. So the first question that we have is, what are scenarios and why do we manage them? We can think of scenarios as variations of our base system to quickly evaluate different changes to our system. So if we imagine that we have a system like this, where we have a single supply tank, and it is going to storage tank A and storage tank B, we might have a range of different options that we want to consider given this specific system. So some of the things we'll look at today is, what if I'm sizing the pipes of this system and I want to compare 2-inch pipes to 1.5-inch pipes? Maybe I can save some money by choosing that smaller pipe size. If we're flowing different fluids through the system, if this is cryogenic transfer, we might be transferring oxygen, we might be transferring nitrogen or fluorine. And then what happens if we are operating, in a range of different cases? Maybe we're flowing to both storage tanks at the same time, maybe exclusively to storage tank A, exclusively to storage tank B. So all of these are kind of minor variations of the same system that we can manage using these different scenarios within our model. So what that'll look like in the software, and what we'll ultimately build to through our example, is building out a scenario manager tree that comprehensively considers all of those different alternatives. So we'll have different scenarios for the 2-inch pipe versus 1.5-inch for each of the different fluid cases, and then also for supply to each of those tanks individually. So we can think of these scenarios as duplicates of the model, where different characteristics that we can change are going to be inherited from a parent scenario, which is going to be more inset, to children's scenarios, which are going to be following the outset. So this 2-inch case, we'll say, is a child scenario of our base scenario. That means that it's an exact copy that we can start our analysis from, and then we can make any tweaks or changes for that specific variation for that specific scenario. So we'll go into that inheritance a little later in the webinar. We'll go through some examples that'll make that more clear. And that's one of the kind of foundational concepts I would want you to walk away with from this webinar is how to set up these scenarios and how to take advantage of that inheritance to speed up your model building process and then also those analysis steps. So the scenario manager, if we want to look at it in the software real quick, you can see that we dedicate quite a bit of space on the right side of our application to the scenario manager. I always think it's funny when people send in a lot of different model files and they only have one scenario in each of them, because all of those things could be consolidated into the single scenario manager. So the scenario manager is what's going to organize all of these different variations. We can see very clearly the relationships between these different scenarios and how it'll inherit those changes, how we can modify them, and what things are we going to test using names and also other tools like the scenario comparison tool. And then ultimately, how can we make those comparisons very easy? One, comparing input to make sure we're only changing what we want to be changing. And then as we run our different cases, how can we compare our output to make sure that we're settling on the most ideal, most efficient, or reliable, or even safe design for our system. So again, scenarios, just think of them as variations of the base system. While you could create kind of unique systems in each of these different scenarios, it's not really the intent of the design. It's really for more minor, small variations that you're trying to assess. So why might you need to evaluate different scenarios? You can imagine me in my best infomercial voice. Has this ever happened to you? The first case, you might need to select pumps for your system that has to meet different design requirements for your different operating cases. So you can imagine if you have different consumers or different seasonal requirements, you're only going to select a single pump that has to work in that full range of conditions. It's important that you can test each of those with that pump. Again, ensuring that it's going to meet those efficiency and reliability expectations that you have for it. So a change in operating conditions, in our example, we'll look at pumping or not pumping, transporting fluid either to tank A or to tank B. That would be a different operating condition we would consider. The second case, a plant is considering an expansion and they want to know if they need to modify any existing infrastructure. For example, they might need to resize pipes or resize equipment. So we might have different scenarios in this case for the system as it is currently, especially if it's an existing physical system. We might model it as the design is laid out. We can adjust it for as it's built and compare it to field measurements, especially if equipment or pipes have degraded. And then from that, that'll give us a basis to model our expansion. If the expansion works out, if our pumps were oversized to begin with enough to justify that, that could be okay. Or as you get further into the design, you might build out additional scenarios. What if I resize these pipes? What if I replace this pump? What if I do both of those things at the same time? So again, the majority of the system would stay the same, but we can isolate and vary and tweak those minor changes in our unique scenarios. So we've looked at different operating cases, expansions or changes to the system. We can also use scenarios for troubleshooting. So we can imagine a pump is having constant reliability issues, causing downtime and expensive maintenance. We've been tasked with determining what in our system is causing issues. So we might build a scenario, again, of the existing physical system. That can give us a baseline expectation of what flows and what pressures should we anticipate. And then we can compare that to field measured data. That can help us identify where issues might be occurring. And once we identify those issues, we can come up with different remedies. So again, you could replace equipment, you could be resizing pipes. All those things you could be considering in those individual scenarios. The final case, let's say we're performing a safety assessment and we want to determine if any combination of failures lead to unacceptable conditions. So we'll look at a specific case study for this kind of example where, especially in safety assessments, if a single component fails, that may be okay. If another individual component fails, that may be okay. And then as you get more complex with more components, more combinations, more things to go wrong, if all those things go wrong all at the same time, that's where it could be that worst case scenario. So we can do sensitivity and explore a lot of different options and combinations to really determine our worst case scenario. And especially for things like transient analysis, where you're designing for surge pressures and extreme forces, you can base those other designs off of that worst case scenario. So those are kind of 4 example cases, but we can generalize them a bit further. And even more so, we can look at what other scenarios you might consider in your own system. So the first case we looked at, you might want to model different scenarios to account for those different operating conditions. There could be different seasonal requirements, like a cooling system in the summer versus in the winter. You might have changing flow demand. You might have an impact to the heat transfer through your pipes because the surrounding environment has different conditions. You might have variable flow demand from peak hours or turning on and off different consumers. Again, any change to your operating conditions like opening and closing a valve, as we'll see in our example. Second case is what kind of changes are we going to make to the physical system? So if we're evaluating an expansion, if we're going to change pipes or if we're going to swap out equipment, we could justify investment to replace or resize equipment. For example, if you were to place a pump and it runs more efficiently or more reliably, that might lead to enough savings to justify paying for that pump. Third case is troubleshooting. So we can look at different scenarios for as we've originally designed it, as it was currently built, or as it's currently operating, and then as measured, and we can compare those different results to identify discrepancies. So we had a case study where a engineering firm built out a model because a pump wasn't able to produce the amount of flow that it was required for a cooling water system. And they were able to determine that a single valve failed directly upstream of the pump. And they could point to that directly, say, oh, we made this change in our model. It reflects the physical system now. This is probably where the issue is occurring. Once you identify the issue, you can then create different options and different scenarios and how to resolve it. Obviously, in that case, you'd want to replace the valve that's failed, but you could also replace pumps, you could replace pipes, anything else, any other change that you'd want to make to your model or system. And then the final case is that transient analysis, where we can also do things like sensitivity. So in transient analysis, think of transient analysis as surge pressures and forces. So if you slam a valve closed, all of that kinetic energy of the fluid suddenly turns into pressure. The more gradual you can slow that fluid down, the less pressure response you should anticipate. And so the easiest variable that you can change is how quickly you're closing that valve. So you might do sensitivity, you might create a range of scenarios at different valve closure times, evaluate them against each other, and figure out that way, what scenario is best or what is going to mitigate those surge issues to an acceptable level. And then as I mentioned, especially with more complex systems and you get these interacting components, you might have a valve closure event that you want to analyze, a pump trip event, and then what happens if you do both of those at the same time. So those are some scenarios you might consider, but anything else that you can think of, you can create as a scenario. Odds are you'll be successful building out a different scenario for each case. Something I do as a support engineer is if someone is sending in a model for me to troubleshoot, usually I'll create a child scenario immediately. I can reassure myself that I can make any changes to that scenario I want, and it won't impact that base scenario or all of the hard work in the original model that they sent in. I'm able to preserve that while still have the flexibility to make tweaks, experiment, pull on strings that I want to pull on to try to identify the issue within a model. So just some inspiration, again, if you probably have scenarios that you consider in your own systems, these are just giving you some more ideas, maybe thinking outside the box. So to reinforce this concept a little bit more, I have 2 case studies that I wanted to highlight. So we get case studies every year through our Platinum Pipe Award competition, which is currently going on now. The Platinum Pipe Award kind of recognizes engineers who use AFT software in 3 different categories: most interesting model, correlation to field data, and then also operational improvements. So this system that we're going to look at was a winner for, I believe, operational improvements and also for the kind of impressive calibration that they work through. So here we are looking at a refinery system that was having flooding issues because their original design kind of under-anticipated or had some core design flaws that couldn't move enough water away from this refinery. So they had all these flooding issues anytime it would rain in Houston. And if you live in Houston, you can imagine it rains pretty frequently. And so they wanted to address these concerns. While the examples we're going to look at today are relatively simple, this is a good case of using scenarios regardless of how complex your model is. Here, if we peek in a little bit further, we can see the complexity in all the valves and other components that they had to consider. So they actually had, I think, more than 100,000 data points that they tried to calibrate their model to. That gave them baseline, and then they could tweak and adjust their scenarios accordingly to try to resolve this issue. So a larger firm proposed a $70 million solution to resolve these different flooding issues. And then this team was able to use AFT Fathom in this case to evaluate different alternatives to try to bring that cost down while still resolving the flooding issues. So their scenario tree looked something like this, where they have their original validated model at the top. That was all of their calibration work, getting the model as close to the physical system as possible, so any changes they would make would be reflected in the physical system if they did implement those changes. And then here we can see that they have a no cost option. If they just change the valve setup, it could improve the flow rate that way, a low cost option, and then a range of different capital cost expenditures. So in the most extreme case, they were able to increase the flow rate by 151%, and they were able to do that at $25 million under what the larger firm proposed. So again, using these different scenarios, building out your model once, and then having all these different tweaks that you can make within your foundational system. The next one we're going to look at is actually their most recent case study. So this came from Lamar University, who we provided a research license as they were doing some surge analysis on liquefied natural gas loading. So for context, their model is the LNG terminal where the liquefied natural gas comes in. It goes through these pumps, through all of these transfer valves, and then it attaches to a vessel where that vessel would then transport liquefied natural gas across the ocean. So their concern is there's a lot of emergency cases that can occur if the seas get intense where the vessel is floating. In a lot of cases, they have to suddenly shut off flow and then disconnect those loading arms. So here's what their scenario manager looked like. They have their base scenario and their steady state. Starting with, if we just look at normal operation, how can we make sure everything is looking promising? And then they had 6 cases for this emergency shutdown case. So in the first case, the emergency system works properly. These vent valves will open to redirect flow since flow can no longer go to the vessel. Transfer valves will close, these other transfer valves will close, and then we'll also trip these pumps, again, trying to reduce the amount of energy that we're adding to the system. Now, if the emergency system works properly, that'd be great, but like anything, the more complexity you add, the more opportunities there are for additional failures. So they had other cases. What if the pumps fail to trip? Now you're closing all the valves and you're pumping against them. What if the vent valves fail to open, so there was nowhere for the flow to redirect? What if both of those things happen, sort of the worst case scenario, and then a mixture of each as well? Something else I found interesting in their model is they have additional scenarios where they were looking at those same cases and they were changing what's called the valve characteristics, or essentially how this valve closure occurs. So a ball valve is going to close very differently from a globe valve or from a gate valve. That's what these different scenarios are trying to consider. So in their analysis, they had all these different cases and they found that the max surge pressure was only exceeding pipe limitations in this worst case scenario. And they could also identify where that maximum pressure was occurring. So the pressures only failed in one case, but they also kind of went above and beyond and assessed the forces. Here's a feature that we'll look at a little later, which is multi-scenario graphing. So they were able to graph those 6 different cases for force versus time. And we can see in case 4, that kind of worst case scenario, we can see that that's achieving the peak force. But regardless, in a lot of these other cases, even if the pressure surge wasn't unacceptable, there's still significant forces that they then brought into another application in ANSYS, and then they could perform their stress analysis. So here they use scenarios again to evaluate combination of different failures and then also sensitivity. What if we change the valve characteristics of the closing valves? How would that impact our surge response? So those are some case studies that again reinforce applications for scenarios. Now we'll go back into the software more so and look at how do these scenarios work. So this will just be the basics of inheritance, and then we'll go through an example which should make it more clear within the software. So the child scenario, if we remember, scenarios are just duplicates of our existing system so that we can make those small tweaks, but it also links parameters from its parent scenario. So if we imagine, here's our scenario tree where we'll have a parent scenario, a child scenario, and then a grandchild, which is created from this child, we can see that the different parameters are going to be passed through because they are just duplicates of one another. So the parent will inherit both the diameter and length if we were looking at a pipe, for example. And then when we create this grandchild, that'll similarly inherit those changes. So any change to a parent scenario will propagate through the generations as long as links exist. So here in this case, we can imagine if we change the length of the parent scenario to 30, that change will be pushed down to the child and to the grandchild because they're all linked together. Because they're kind of generationally linked, any change to this parent scenario will be pushed down. If we take a look in the software, which might reinforce the concept a little bit further, here let's say that we have our existing system, and for now our tank is pressurized to 450 psi-G. When we create a child scenario, which we can do by right-clicking the base scenario, create a child, we'll call this our child. We can see that it's going to inherit everything from our original scenario. If we were to run these two cases, they would be exactly the same. If we make this the grandchild scenario, we're again just creating an exact duplicate of this case, where again, all of our parameters, not only for the reservoir, but for the rest of the system has been brought over as well. So now if we make a change to our base scenario, everything is still linked together. They're all exact duplicates of one another. We haven't, for example, broken a link, which we'll look at next. Any change that I make to this base scenario will be pushed down to the child and to the grandchild. So if I make this 500 psi-G now for our surface pressure, I can hit OK. And now when I go into the child, I can see that it's inherited this 500 psi-G surface pressure. The same thing with the grandchild. So we can use this to our advantage. Let's say that we build out our big scenario tree and halfway through our analysis, we realize that we misspecified something. We can go back to our base scenario, we can make that modification, and then it will go and transmit down to all of our different children scenarios. So that's kind of the most basic idea of inheritance. Each of these child scenarios is an exact copy, and as long as we don't break those connections, it'll continue to inherit changes that we make to the parent scenario. In the same way, if I make this child scenario now 550, we can see that the grandchild will inherit that change to 550 psi-G. So making a change in the child compared to making that change in the base scenario is going to lead to a little different result, because making that change is going to break any links that exist with the parent. So here in our kind of conceptual example, let's say our parent had a diameter of 3 and a length of 30, and then in our child scenario, one of the cases that we might be analyzing is what if we make this pipe bigger? We will break the link to that parent, but the grandchild will still inherit that change to its parent scenario. So because the child scenario is the grandchild's parent, it will inherit the change still. It's maintaining this link. Note that this is specific to the parameter, so all the other parameters will remain linked. If I make any other change in the parent scenario, it'll still be pushed down to the child, which will then continue to the grandchild. So in software, what this will look like, if we remember, we changed our child scenario to 550 psi-G, and our parent scenario, or our base scenario, is still at that 500. Because the change that we made to the child is not going to propagate upward, it'll only ever propagate downward. If I make any other changes, like back to 450 psi-G, because I've already made this change to the child, it's not going to overwrite that. So it's important to have an understanding of where those changes are occurring and where within the scenario structure the changes have occurred, because of this inheritance conditions. And later in the webinar, when we look at the scenario comparison tool, it'll make it very easy to identify where those changes have occurred in those different scenarios. So stay tuned for that part. So here we'll delete this scenario, we'll delete its children, and then we'll have our base scenario for when we start doing our analysis. We have some great examples if this is still a little bit less clear, which give you a model and give you the changes to make, and then it'll demonstrate a lot of these same concepts in a little bit more detail. Again, seeing kind of the range of user experience, it's challenging to kind of be comprehensive, but hopefully this little example and some of the examples that we'll do here in a moment will make these concepts more clear. So these are the basics of inheritance. We can use this to our advantage as we design different experiments or why we would want to build out these different scenarios. If we think back to our high school science class or middle school science class, a good experiment should really only have one independent variable at one time. We want to tie any change to that variable to the change in output or the change in the effect on the system. So if we have multiple variables at the same time, now we're going to start doing more complex sensitivity analysis where we want to do a wide range of conditions. So we can still do that in the scenario manager. And if we put some thought into it, we can build some structure, and that'll help us build our different alternatives efficiently. So imagine we're back on our cryogenic transfer system. And in this case, we want to size our pipes. So we want to compare 1.5 inch and 2 inches. And we have a minimum flow requirement that we want to meet, and we have a lot of different operating conditions that we're trying to consider as well. So through this same system, we're going to flow either nitrogen, oxygen, and fluorine. Because they're different fluids, they're going to have different fluid properties. That means different pressure and flow rate distributions as well. We will only flow to either tank A or tank B at a time. So that means that we're flowing nitrogen, oxygen, and fluorine to tank A. Those are 3 of our cases. And then nitrogen, oxygen, and fluorine to tank B. Those are another 3 cases. We have a minimum flow rate requirement. So that's how we're going to be evaluating these different cases. And we want to consider either 1.5 inch or 2 inch pipes. So for our 3 fluids with flow to tank A, our 3 fluids for flow to tank B, we now have to do that assessment for both 1.5 inch and 2 inch pipe. So you can imagine going through this one by one, making individual files. It's going to be a lot of information, but we can structure our scenarios to make it pretty simple to evaluate all these different cases. So one question that I would try to answer before doing this type of analysis is how many unique scenarios do we need? So we have 3 different fluids. We have nitrogen, oxygen, and fluorine. Each of those fluids have 2 unique operating conditions for flow to tank A and flow to tank B. And then we're going to be evaluating 2 different pipe sizes for all of those different cases. So in total, we're going to be trying to build out these 12 different scenarios. And you can imagine, again, more complex, the more interactions that you have, the more scenarios that you're going to be building out. But we'll go through an example trying to build out these 12 scenarios and showing you how it can be done very efficiently. We'll try to shoot for within the next 5 to 10 minutes. We'll see if we can make it. And again, this will also reinforce those concepts that we saw with how scenarios are inheriting different changes. So back in the software, the first thing that I'm going to do is have an understanding of where my system is starting from. We will build some redundant scenarios just for organization's sake, but we could save some scenarios as we create the tree if we put some forethought into it. So if we take a look at model data, you can split the screen like this by grabbing the tab and moving it over. So for example, you could grab output and you can move it over here. All I'm doing that for is so I can have model data on the right and a view of my workspace on the left. If I zoom in, we can see on the pipe section that we are looking at 2 inch pipes. So because my system is already defined in 2 inch pipes, I'm going to create a child scenario and we'll call this 2 inch. So here in model data, what it's doing is comparing my scenario input. So here we can see that these are all the same. I'll turn that off real quick from model data control, which is this pencil with a little book here. And for my scenario format, I'll just make this for current scenario only. That should be the default setting, so it should just look like another, again, duplicate of my base scenario. So we have our 2-inch case. The next thing that we're going to look at are the different fluids. So if I go to the system properties, we can see that our existing fluid is fluorine. We'll hit OK. And so the next child scenario I'm going to make is fluorine. If I could type, let's see, fluorine. So here we have our 2-inch, our fluorine, and now the next thing we're going to look at is those different operating cases for flow to A and flow to B. So we'll create another child scenario. We'll call this flow to tank A, where this is really the first change that we're going to be making to the model. So now for flow to tank A, we're going to close valve B, which we can either do from this toolbar up here. From the special conditions, we can mark that closed. Or if we go into the valve properties window by double clicking, we can go to the optional tab and change the special condition to closed. Since it's already closed, we'll just accept that change, hit OK. So now instead of creating another child scenario for flow to tank B, I will create a child from this fluorine. That will make flow to tank A and flow to tank B sibling scenarios, which don't impact each other. If I were to make a change to a sibling, it's not going to be inherited like a child. And here we'll call this flow to tank B. So now we can switch it. We can close valve A, again using this special condition to close it. So far we have 2 of our 12 scenarios. We have the 2-inch fluorine flow to tank A. And if we double click it, we can see that valve B then closes. And if we go to flow to tank B, now valve A is closed. So the next thing we're going to do is clone some of these scenarios. And what that's going to do is bring over these child scenarios, and it'll inherit the changes that we make. So because I want to analyze another fluid, what I'm going to do is right-click fluorine, and I'm going to use this option, clone with children. What that's going to do is create a clone of that scenario. And here we'll look at it with oxygen instead. And we can see that it brings over our child scenarios for flow to tank A and flow to tank B. So if we go into those, again, valve B is still closed, valve A is still closed. And now if we go into this parent scenario for these 2 cases, we can update the fluid. So again, in the fluid properties window, we can search for oxygen, which you can jump to just by pressing O for oxygen. We will add that to our model. We'll replace fluorine, and we'll set that to -292 degrees Fahrenheit. So now if I hit OK, because I've made this change in this parent scenario, it will transmit down to these children scenarios. So if I go into here and I go look at my fluid, I can see now it's updated to oxygen. So just that one change has now pushed to all of my different cases. So we'll do the same thing one more time with nitrogen. So again, we're going to right-click this parent scenario, clone with children, and we'll call it nitrogen. And we will update our fluid to nitrogen. -292 degrees Fahrenheit. Hit OK, and then in these child scenarios, we can see that we're still using nitrogen, even though we didn't make that change in that specific scenario. So the next cool thing that we can do is now we have 6 of our 12 scenarios. We can see that it's moving pretty quickly. We can do the same thing to clone with children, but now we're going to clone with children this 2-inch case. So when I clone it with children, we'll make our change for the 1.5-inch pipes. And now we can see how when I make this change in this parent scenario, it'll be pushed down to all the different cases that I want to analyze. So again, by understanding how those changes are going to be inherited, we save ourselves a lot of time avoiding that redundant input. So to make this 1.5-inch change, because I want it to push down to all these children, I'll make it in this parent scenario. We're going to use the global edit tool. So to global edit, first I select all the different pipes that I want to update. And then here I can use this global edit icon, and I'm going to perform a global pipe edit because I'm editing the pipes themselves. So when I click global pipe edit, here we have this guide on the right because there can be quite a few different steps. So if you ever get lost, you can follow these in sequence. In our case, we're going to be using the pipe template, and we're going to select our pipe data. This is just a generic pipe properties window, so that any change I make to this pipe, we can apply those changes to the pipes within our system. So our pipe material in this case is stainless steel, and I want to set it to 1.5 inches, and the type we're going to set to Schedule 40. So because this is the only change that I'm going to be making to my pipes, I don't have to specify a length, I don't have to modify friction model or anything else here. When I hit OK, here are the parameters that are available for us to apply to our different pipes. I can click this nominal size, we'll apply the material as well, and we'll transition from our 2-inch pipe to this 1.5 inch. So all the pipes I want to change are selected, all the changes I want to apply are selected. I can apply my selections. If I click OK, now what I can see is all of our pipes are 1.5 inches in diameter. So with that one change, I was able to modify all 5 of those pipes. You can imagine in an even more complex system, global edit can save you a lot of time in terms of modifications. So again, here we've changed it in this parent scenario. So if we go into this child scenario, we can see that that 1.5 inch pipe change, again, has transmitted all the way down here. So from an organization structure, we have our 1.5 inch cases for our 3 different fluids, and for our 3 fluids for each of the flow conditions. And if we counted these up, here we have our 6 cases, here's our other 6 cases. These are the 12 scenarios that we were hoping to analyze. So again, understanding the scenario manager, understanding the inheritance gives you this flexibility to make all of these alternatives very quickly. And also we'll look at the additional features to confirm that the changes we made are as we intended. So before we run all these models and assess the output, we'll look at some different tools for managing scenarios. Obviously, Scenario Manager has its own tool set. These are kind of in addition or different ways that we can assess them. The first tool that we'll look at is the Scenario Comparison tool, where we can identify differences between our scenarios. This is what the interface will look like, where we can select different scenarios to compare. And then it'll give us a report of what's changed between those 2 cases. So in the software, you can access this 2 ways. You can either right-click on the scenario tree, you can go to the Scenario Comparison tool, or if you go to the Tools menu at the top, you can also use the Scenario Comparison tool. So the Scenario Comparison tool, again, here are all the different scenarios that we've created, and we're going to select the 2 that we want to compare. So for our 2-inch case, let's say we want to compare our flow to tank A of fluorine and our flow to tank A of oxygen. So it's important to think the only change that should be occurring between these 2 cases is the fluid. So we can use this comparison tool to confirm that that's our suspicion, especially if we're getting kind of unorthodox results as we're doing our analysis. Here you can change the different properties that you're reviewing. Personally, I prefer to just leave them all involved, because as we'll see, we can highlight only the differences, and that'll isolate the differences for our comparison. So if we click Show Comparison, here what we see is our 2 scenarios represented as different columns. If we hover over them, we can see that we have our base scenario, 2-inch fluorine with flow to tank A, and then our base scenario, 2-inch oxygen flow to tank A, where the only difference between these 2 cases is the fluid itself. So this is working as intended. We designed our scenarios as we were supposed to, and we're isolating only that factor between these 2 cases. If you wanted to show all parameters and all items, again, this is another way that you could check, but really it's primarily for comparison, hence the name Scenario Comparison tool. We can modify our comparison with this button here in the lower right. And here we can make a spicier comparison. So let's look at our 2-inch fluorine flow to tank A, and then we'll look at nitrogen flow to tank B for a 1.5 inch case. So now we're changing all of our variables. We should see a more rigorous differences as we do this comparison. So if I go to just differences with these toggle switches, here we can see that all of our pipes have been reduced to 1.5 inches in the second case. and our valve special conditions have closed or have changed, again, because that's how we're controlling our flow to our different tanks. And then our fluid properties, those have also changed because we're testing our different fluids. So I found this very useful for troubleshooting, especially if you get kind of lost in the weeds of your own scenarios and you're not sure what you've changed or what has, converted a problematic system to a working system. You can use this to compare to your base scenario, identify all of the different changes that you've made. So that is the scenario comparison tool. The next thing we'll just bring awareness to, we won't formally save a file, but you can also save these scenarios to different files. This is useful to isolate particular scenarios if you're sharing it with a colleague or if you're giving it as a final deliverable, especially if your scenario manager gets kind of hectic. We can do this from the right-click menu, where you can right-click a particular scenario, and then you can save the scenario file with its children or just that individual scenario. So very useful just to isolate cases. For example, if you're sending in something for troubleshooting and you don't want to point us through your chaotic scenario tree. Again, within the software, just right-clicking on the scenario, and then down here, save scenario with children or without children, and that'll create a new unique file. The final feature is batch run, which allows us to run multiple scenarios back to back. With the 12 scenarios we've created, you can imagine it'll be pretty tedious for me to run one, wait for it to finish, go to the next one, run it, wait for it to finish. So batch run will let us select a full range of scenarios, and then we can run them all in sequence in the background. So we want to run all of these 12 scenarios so we can compare our output. Before we do that, I'm going to add a design alert for our flow rate requirement. Design alerts are also going to be inherited by scenarios in the same way. So if I make a design alert in the base scenario, it'll check those conditions in all of our child scenarios as well. So from the tools menu, I can go to design alerts, where design alerts are just like a user specified warning if a variable goes out of spec. So if I create a new design alert, we'll call this minimum flow rate, 30 GPM. I want to check the flow rate in different pipes, but you could also check them in pumps, valves, heat exchangers, and reservoirs. And these give you more flexibility for different variables that you can check. Here I want to look at the volumetric flow rate through the pipes. And I have a minimum flow rate requirement of 30 gallons per minute. So I can add this to the list. If I had other things to check with the same design alert, I could list those as well, but we're keeping it relatively simple here. We will add our design alert. So now this is just a generic check, and we have to tell it which pipes or where in the model we're checking that. Since sometimes we'll have flow to tank A, and sometimes we'll have flow to tank B, the best place to check is in pipe 1, since that'll always see the full amount of flow going to either tank. So if I select pipe 1, I can hit OK, and that'll apply to all of our different scenarios. So because of our design requirement where we need to meet that 30 gallons per minute, we can automate that process within Fathom to check, which is especially useful as we start doing our batch run and comparing all of these different scenarios. So we'll collapse these tabs real quick. To access the batch run, you can go to File and then Start Batch Run. That'll bring us to this batch run window where we have to select our different scenarios that we want to run. You can also run multiple models at the same time if you're doing that kind of layer of complexity. So here we can add our different scenarios. One of the things that I think is neat are these options to select scenarios with output or without output. So I only want to run things that I haven't run already. I could use this selection. In this case, we'll just manually click through our 12 different scenarios. So all of these are going to run in sequence. If we hit OK, a feature that we added in the latest versions is this run batch in the background. So if I check this, when I go and start the run, it'll go through this whole process of running the background, and I can go to a different window. I can go do other work without it bringing my kind of attention back to the batch run as each scenario completes. So just a small usability thing that improves quality of life as a user. So here we can see the results from our batch run. it ran relatively quickly, and we can see that they all ran successfully. And here we can see in some cases that our design alerts were triggered. But all runs were completed without errors. We didn't have convergence issues or any other problems that we need to be aware of. So when we close it, now we can see that all of these scenarios have our output. And again, the process of creating those 12 scenarios, running the batch run, and then what we'll look at here with the analysis, that can all be performed relatively quickly if you know how to take advantage of those inherited structures. So again, scenario comparison tool, useful for comparing input and identifying the changes between each scenario. Saving scenarios to file, useful if you need to isolate or simplify your model and isolate a different scenario. And then batch run, if you are taking advantage of it and you have a lot of cases and they take a long time to run, you can select multiples, run it in the background as you complete other work. And again, batch run found from File, Scenario Manager, right-click, and the Scenario Comparison tool, either right-clicking the scenarios or going from that tools menu. So now that we have all of our output, we can look at different options for analyzing our different scenarios. First is multi-scenario output, where we can centralize all of our tabular output for each of our scenarios and build them all out into one table. What that'll look like in the software is we can have, here's pipe 1 results for our normal output, flow rate, velocity, static pressure, everything else that we'll look at. And then we can see for each of our different scenarios stacked one on top of the other. So if we were checking for volumetric flow rate, for example, and we were only trying to maximize volumetric flow rate, we could say this particular scenario is going to do it for us. To do that in the software, these settings are scenario specific as well. So if you make this change in this particular scenario, because this is kind of a final child, it's not going to be inherited by any of the others. But if we make this change in the base scenario, it would be updated in all of our children as well. So here I'm arbitrarily selecting a scenario. It won't actually matter because we have to pick the scenarios that we're going to show. And if we go to output, this is just what normal output looks like as you're doing your analysis. The setting we want to use is multi-scenario output, which we access from this output control button here in the upper left with the pencil and little spreadsheet. That takes us to the output control window. And here this final tab is multi-scenario. So by default, we always show the current scenario, but we can select different scenarios, where again, we can see our full scenario tree. Here I want to show everything with input. So it's automatically selected my 12 that I want to compare. And if I click OK, here's all 12 scenarios that I'll be able to evaluate all from one table. So now if I click OK, we'll close up some of these windows just to get a better view. And if we zoom in a little bit further, again, we can see here's all of our pipe output for pipe 1 for all of our different scenarios. If we were checking by hand, we could say this scenario fails our flow rate requirement, this one and this one. Or with the design alerts that we have defined, we can also see that they're centralized up here. So up above our pipe output, we can see here's all the design alerts that are reported for each scenario. And here we can see in these 3 cases that it did not meet our minimum flow rate requirement. So multi-scenario output, very valuable if you're invested in the tabular data and you need exact numbers. Again, compared to jumping between each of these scenarios, trying to bring it into Excel by hand for your own comparison. You can also select all of this and copy it and bring it into Excel as well, because it should play nice with, the spreadsheet format that our output is put into. So that is multi-scenario output, again, accessed from output control here in the upper left and the multi-scenario tab here at the final end. By default, it'll show only your current scenario. We want to select different scenarios where we can use this feature to select with output if we've just gone through and run all of our different scenarios. So the next feature is something that we actually saw in that case study already, which is multi-scenario graphing, where instead of looking at tabular output, we can compare responses visually. So we have features for multi-scenario pump versus system curves. This isn't something that I'll go into in this particular webinar, but if you want, you can go to our website. Let me pull it up real quick. where I've written a tips and tricks blog. So if you go to AFT, you go to the Learning Center, tips and tricks. So the name of the blog that I wrote is Getting There is Graph the Fun. Is graph the fun, because you're making a graph, get it? And so if we search it, this will take you through the steps to make those multi-scenario pump system curves. So the process is a little intensive, but it can be intuitive, especially if you're combining it with batch runs, but just not something that we'll cover in this particular webinar. Of course, if you have questions or if you want to link to this directly, you can shoot us an email at webinars@aft.com, and we'd be happy to send you a link. The other type of graph was added, I believe, more recently, which is multi-scenario graphing for more typical graphs like profile graphs in Fathom or Arrow, transient graphs in XTS or Impulse or Extreme, and then also profile animations. So we'll look at a quick example here. This is what we saw from our case study where they had the force response for their 6 different cases of their LNG emergency shutdown, where again, they can plot them all on the same graph to get a better understanding of what's going on within their system. So in our model, what we'll do is go to graph results. And here we'll make a quick profile graph by selecting our pipes that we want to follow along with. So we'll look at the pressure distribution through these pipes and compare them across our different scenarios. So if we go to our graph results, since I've selected those pipes on the workspace, I can use this workspace selection. I can click generate. And here we see the static pressure for our current scenario. So since it's closed off, we don't see any real change in our static pressure due to frictional losses. We can select multiple scenarios using this multi-scenario button, where here again we can select our different cases. So if instead of nitrogen I wanted to look at oxygen and fluorine, I can hit OK, regenerate my graph, and now we can see those different scenarios have appeared. So this isn't a very extreme example, but you can still see the difference in results for those different cases. So it's a very intuitive interface in my opinion. So just having this multi-scenario option as you're making your graphs normally, and then you can select the different scenarios that you want to include in your graph. The final feature is Excel export. So this is more of an awareness rather than going through the process of creating an Excel export and exporting it for our different scenarios. But you can specify different parameters that you want to automatically export to Excel. I think it's funny because one of the main arguments for our software is to get away from spreadsheets, particularly for your hydraulic analysis. But like everything in engineering, you're almost always inevitably going to end up in Excel doing something. So to access this window, you go to File, and then the Excel Export Manager, where we can open it up. We can specify different things like a value for a particular pipe. So if I wanted to isolate the lengths of my pipes, for example, and export that to Excel, we could do that. And then along with batch runs, you can export them for different scenarios and then export that automatically during your batch run. So as it finishes a run for each scenario, it'll look to this Excel Export Manager, export it to a spreadsheet, again, helping you automate that process, even though the copy and pasting from output can be helpful. So tune into a future webinar, and if you're watching a recording, maybe that webinar is already out and you can dig around in our YouTube channel for that recording. So those are some of the tools for analyzing our scenarios. Again, multi-scenario output for tabular output, updated from the output control window, multi-scenario graphing, where I would refer to that blog if you have more interest in how to make a multi-scenario pump versus system curve, and then the normal graphing for profile graphs or transient graphs or other animations is pretty intuitive. And then Excel export, which we won't go into too much detail here, but tune into another webinar to learn more about that feature. So we made it to the summary. Hopefully everyone has learned something so far, but we'll go through and kind of review the ideas and the topics that we discussed over the past hour. So The first thing is there's many options and alternatives to consider while doing hydraulic design and hydraulic engineering. We looked at all the different scenarios we can compare for operating conditions, changes to infrastructure like replacing pipes or replacing components, and how we can use sensitivity analysis like the 12 scenarios that we built out to try to find the best, either most efficient, most reliable, or safest system for our design. The scenario manager gives engineers flexibility to organize and modify these scenarios quickly. Again, thinking about how we can put some forethought in, use the clone feature to especially do sensitivity analysis, and then also how those scenarios will inherit those changes. So having a good foundational understanding of that makes you a more powerful engineer and makes you more productive as you're doing your modeling. We have a range of different tools that can help you compare scenario input, so the scenario comparison tool, or if we wanted to run all of our different scenarios at the same time, we can use a batch run. So the scenario comparison tool, again, from the tools menu, and then batch run from the file menu. And then finally, putting some forethought into how we structure our scenarios can save a lot of time, especially as our analysis gets more and more complex. So the more components we're considering, the more options, the more analysis that we're doing. Think about how you're structuring your scenarios. Make sure that it's clear not only to you what you're changing in each scenario, but also it's clear to anyone that might inherit your model in the future. So I want to thank everyone for attending, especially if you've made it this far in the webinar. Again, there was a lot of kind of basic concepts, but hopefully even as an experienced user, you learned a new feature or something neat that you can incorporate into your own modeling. If you have any remaining questions, or if you're looking for a link to any of the things that we talked about today, you can shoot us an email at webinars@aft.com. We'll do our best to get you a response by the same day. And then if you have any ideas for future webinars, you can always submit a topic to webinars@aft.com. It's always exciting seeing users attend our webinars, and hopefully we learn something new and then seeing them apply it in their own models. And so we look forward to having you in another future Applied Flow Technology webinar soon. Until then, we wish you the best, and we look forward to having you again. Thanks.